Problem number 23. A mass is attached to an ideal spring at time t equals 0. The spring is at its natural length and the mass is given an initial velocity. The period of the ensuing one-dimensional simple harmonic motion is t. At what time is the power delivered to the mass by the spring first a maximum? Solution. To solve this problem, let's just write the equation for harmonic motion for this mass. Using initial conditions, we can write it like this. Displacement equal amplitude multiplied by sine omega t. Second, we can count what is velocity, just to take a first derivative by time. That will be this expression, a omega cosine omega t. Second, we do a second derivative to find what is acceleration. That's negative a omega square sine omega t. And now we can count what is power. Power equal force multiplied by velocity. This one. So force equal mass multiplied by acceleration. And using these two formulas, we can count what is power. That's negative 1/2 a square omega power 3 sine 2 omega t. And now we need to find what is at what time first this power has a maximum. That's obviously for sine 2 omega t equal negative 1. This one. And the first time it happened when 2 omega t equal 3 over 2 pi. And from here we can immediately find the moment when this power has a maximum. This is the solution. So time equal 3 over 8 period. Here in these 5 answers, we have to pick the correct one. Correct one is D. Time equals 3 over 8 t. Problem number 24. A uniform rectangular wood block of mass big M with a length b and a height a rests on an incline as shown. The incline and the wood block have a coefficient of static friction mu s. The incline is moved upwards from an angle of 0 through an angle theta. At some critical angle, the block will either tip over or slip down the plane. Determine the relationship between A, B and mu s such that the block will tip over and not slip at the critical angle. The box is rectangular and A not equal B. Solution. Let's draw the picture for a critical position when angle is critical and block is not yet tipped over but almost ready. So that's the picture. I can remind you that critical angle is an angle for which this block start to slip when tangent theta equal mu static. And also critical position here because we have a center of gravity, which is center of mass, and the vertical line going through this center of mass is going exactly through one corner of this block. It means that after it will move a little bit further, it will slip over because there are no support from base of this cube. It means that we can just count what is the geometry for this picture. Here we have angle theta, which is critical, and also we have angle theta here, because we have two perpendicular lines which are forming these two angles. And the tangent of this angle theta in a cube exactly equal b over a. And we know that this tangent equal mu static. So this is our formula. It means that this cube will tip over when tangent theta or mu static greater than b over a. That's the answer for question, which is C. Problem number 25. Two disks are mounted on thin, lightweight rods oriented through their centers and normal to the disks. These axles are constrained to be vertical at all times, and the disks can pivot frictionlessly on the rods. The disks have identical thickness and are made of the same material, but have differing radii r1 and r2. The disks are given angular velocities of magnitude omega1 and omega2 respectively, and brought into contact at their edges. After the disks interact via friction, it is found that both disks come exactly to a halt. Which of the following must hold? Ignore effects associated with the vertical rods. Solution. First, we can write equation how is angular momentum changing during time. Suppose that force of friction Fj act on both disks for the time delta Tj. They act to each disk, so these two forces, they are equal to each other. And the change of angular momentum equal this expression: force multiplied by radius multiplied by delta time. And I equal 1 or 2. That's correct for both disks. Now we can summarize all this interaction till both disks came to halt. So it means that total change of angular momentum equal total initial angular momentum. It means that we have this formula. So for both I, we have this sum the same for both disks. It means that we can divide this angular momentum for first disk by angular momentum for second disk and have this relation. What are this initial angular momentum for both disks? They are like this. Angular momentum equal I multiplied by omega, and the I equal 1/2 mass r square, and because mass is proportional to radius square, we have this formula, and finally this is the expression for angular momentum. Now we can divide this angular momentum for the first disk to angular momentum for second disk and equalize it to this expression. So after dividing this L1 over L2 for this expression, we have this relation, and it's equal to initial relation R1 over R2. We can cancel one time R1 and R2, and finally we have this relation. We have R1 cube multiplied by omega 1 equal R2 cube multiplied by omega 2. This is the solution. And that's answer number D. Correct answer.